by studying question 2 in group 1 of section 1.1. And it says follows. Show that A union B is equal to A intersect B if and only if they are the same sets. And then a follow-up question is it true that A union B is equal to A and A intersect B is equal to B if and only if A equals B? So take a couple seconds to try this out, and I'll give you some hints in a minute. Alrighty then, for some hints, for this first biconditional, try proving it in both directions, just breaking it up, don't try to do it simultaneously. And in particular, the reverse direction is a lot easier than the forward direction. Likewise, for the second half, since they're asking is it true, you might want to see if it's actually false, if there's a good counterexample to this. And if there isn't, then try to prove the biconditional in each part. Alright, let us begin. So let's start with the first one. So for this first biconditional, let's prove the biconditional in both directions. And for the reverse direction, let's assume A equals B. Well, if the sets A and B are equal, then A union B, namely all of those sets that are in A or in B, are merely those elements that are in, the set of interest, A or B, however you want to label it. So that's all of A. But if you look at A intersect B, that's all the elements that are in both the sets. But since they're equal, they share every element. So every element in one is an element of the other. Therefore, A intersect B is just the set itself. So we've shown that the two sets are equal. Now let's try proving the other direction. Let's try to prove if A union B equals A intersect B, then we're going to have it that A is equal to B. So A union B, those are the set of all elements that are in either A or B. And that being equal to A intersect B, namely the set of all elements that are in both of them, means that if anything is in the union, that means if anything is in either of them, then anything's in both. So you'd think we're maybe done there, but we can be a little more precise, and we can say if an element is in A or B, means it's in A and B. Let's choose some element A that's in A. Then if A is an element of A, then because it's in the union, and the union is equal to intersection, then we know that A is an element of B. But that's true for any element of A. Therefore, since every element of A is necessarily in B, then we can say that A is a subset of B. But then we can perform the same process and start with some B in B, and that's going to be in the union. And therefore, since the union is equal to the intersection, it must be the case that that B is also in A. So we can show, by the exact same logic, that B is a subset of A. And now, since we have subsets in both directions, they include that A equals B. Fantastic. So let's start with the next section, or the next question. Is it true that A union B is equal to A and A intersect B is equal to B if and only if A equals B? Well, kind of as might be suggested by the hint and the phrasing, this is not necessarily true. So we can cross that out. I can show this by a counterexample. Let's let A equal the set of 1, 2, 3, and B just be the set including the element 2. Well, clearly, A union B, everything that's in A or B, is all of A, because 1, 2, 3, or 2 is simply 1, 2, 3. But A and B, A intersect B, is clearly just 2, because the only thing that is in both of them is just 2. However, it's not the case that these are the same sets, because, for instance, A includes just 1. However, the reverse direction of this is true. If A equals B, then we could say that A union B is equal to A, or B, if you want, and A intersect B is B or A. But this forward direction does not hold, as this counterexample shows.